is lecture 10E on polar coordinates. In the first lecture on chapter 10 we talked about parametric equations, and in general we used the variable t for the parameter. It wasn't necessary to have t be the parameter, but that was actually very common, and sometimes it's very handy, especially if you have something that's moving or changing with time, that you would use t as a parameter. There is another, which I'm calling a famous parameter, and this is the angle, the central angle at the origin of the Cartesian coordinate system, and it gives rise to what are called polar coordinates. For this particular parameter, moving from the Cartesian to the parametric, or what is now called the polar coordinate form, is particularly easy. So here is a diagram of what we're doing. The parameter is theta. Right. Using the trig functions, x is r, meaning the radius out to the point P, times the cosine of theta, and y is r times the sine of theta. If you want to change from Cartesian to polar coordinates, r squared equals x squared plus y squared, the Pythagorean theorem for the right triangle, and theta is the arctangent of y over x. So that becomes a relationship between the two parameters. The parameter theta, r, is considered a function of the parameter theta and the xy variables in the Cartesian system. In the past, you might have just thought of polar coordinates not as in terms of as a parametric equation, but just as another form of writing equations. But really, the r is considered theta, and theta is considered the parameter. Okay, just to practice changing from polar coordinates and to Cartesian back and forth, say you have the polar coordinate form where r is tan and theta is pi over 2, then x, 0, y is 10, just by substituting into the forms x equals r cosine theta and y equals r sine theta. If x and y are 4 and 4, you can find your polar form. R equals 4 root 2 and theta is pi over 4. Because you're using the arctangent function, sometimes you have to make adjustments for tangents for the quadrant. So for a point in quadrant 4 where x and y are minus 4 and minus 4, r is the same, 4 root 2, but theta, the arctangent, is pi over 4. But to adjust it for the quadrant, we would have to add pi. Theta is then 5 pi over 4. I'm sure you're adept at going back and forth between polar and rectangular coordinates from trig. So briefly, I'm sure you know how to locate these points. In polar graph paper, here's your polar graph paper with the angles marked off in degrees. The polar axis is this line right here, the positive x-axis, and the point of 0 radius is called a pole. If we want to look at polar coordinates as a parametric equation, then we consider the radius. We can isolate it in the polar equation. We can isolate it, then the radius is a function of theta. So polar coordinates are now parametric equations. So when we write our equations for x and y, x is r cosine theta, but r is some function of theta, so we see we've written a parametric equation here for x in terms of theta. Here's the parametric equation for y in terms of theta. All of the forms for calculus that we develop for parametric equations we will also develop for polar equations. For the derivative, dy by dx, the derivative along a curve in the xy plane, in terms of a parameter t, would equal dy by dt over dx by dt in this case, since theta is the parameter, is dy by dx divided by dx, dy by d theta divided by dx by d theta. Right? To take the derivative of y with respect to theta, remember that r is a function of theta, so y equals r cosine theta, where r is a function of theta. We must use the product rule, so we have the derivative of r with respect to theta, leaving sine theta alone, and then we leave r alone and take the derivative of sine theta and get cosine theta. For the x-coordinate, dx by d theta, again you have a dr by d theta term, leaving the cosine theta alone. using the product rule. The r is now held constant, and we take the derivative of cosine theta and get minus sine theta. So combining this, we have the Cartesian derivative in polar coordinates. So if x and y are expressed in polar coordinates, the slope dy by dx equals dr by d theta times sine theta plus r cosine theta divided by dr by d theta times the cosine theta minus r times the sine of theta. We don't have to rederive it, we can just use this result now that we know it. For the arc length, the general expression in terms of parameter, say theta, would be the arc length from theta 1 to theta 2, square root of dx by d theta squared plus dy by d theta squared integrated with respect to theta. We know dx by d theta and dy by d theta from the previous slide. When we put those together, we would have this for dx by d theta. Remember, you get the negative sign there for the x. And here is dy by d theta. If you expand and work out the terms, you see that quite a few cancel thanks to that negative sign. We end up with something fairly simple, r squared plus dr by d theta squared. Thus the arc length in polar coordinates is the integral from theta 1 to theta 2 of the square root of r squared plus dr by d theta squared. Of course, the arc length differential follows directly from that. And when we're looking for the surface area of a figure of revolution about the x-axis, if it was all expressed in polar coordinates, the surface area is the integral of 2 pi y ds, but we know what y is. Y is r sine theta, and ds is from the arc length function right here. Oops, I didn't get the pen, sorry. And we substitute that, and that's our expression for the arc length in polar coordinates. To find enclosed area, it's particularly simple in polar coordinates if you have the expressions in terms of r and theta, because the area of a sector is 1/2 r squared times theta. But r can vary with theta, as shown here. In this particular function, you see r would vary with theta. Longer here, a little bit shorter over here. Okay, so r is a function of theta. So this turns into an integral. Of course, we could do the usual thing where we divide the graph up into slices based on angle. Apply this formula here for each little sector as though, whoops, sometimes I think I pick up the marker and I don't get it. But that's the area of a little sector in which the radius is constant in that sector. Then add them all up and take the limit, the usual calculus drill, and we end up with the definite integral. In this case, we're integrating again from theta 1 to theta 2, 1/2 r squared d theta. And r is that radius, which is potentially a function of the angle theta. So that's, in a nutshell, polar coordinates and the calculus associated with polar coordinates. And all we did was take the expressions that we had for the parametric equations and evaluate them for polar coordinates, and we ended up with some fairly simple expressions that we can now use.